Hi Shri, my name is Tisuri and this is my video project for structural analysis in semester 2 2019. So this is the structure that was the subject of my project. It is a footbridge that is located at the kids playground in Harbour Esplanade, Docklands. So this is a picture of the bridge and I've marked the measurements I've taken for it. So to start off, I classified my structure as a group 1 structure because it is a bridge. And as for the supporting conditions of my structure, it has 2 pin supports at the either end of it. So here I've sort of deassembled it into substructures to identify the beam elements. And so here I've given the main beam element and I've marked the dimensions of it. So here's a diagram that gives the triangular distribution of load that I'll be assessing for my calculations. So to start off my calculations, I drew a free body diagram which is given here, and I drew it so that it would help me to find the reaction forces for my structure. So I decided early on that I would use point A as a zero as at like a starting point for my shear force and bending moment diagram. So A would be 0 and going up to B it would be 9.7. So having that in mind, I really only needed to find AY to draw my shear force and bending moment diagrams. So to find AY I used the sum of bending moment around point B being equal to 0, and that gave me AY as being equal to 37.68 kilonewtons. Then I considered an arbitrary segment of my beam at a length of x from point A, as I mentioned earlier. So to find the distribution load of y, I used similar triangles which gave me y being equal to 2.4x. And then to find the equation for the shear force, I used the sum of forces in the y direction being equal to 0, which give me the equation for the shear force as being 37.68 take away 1.2 times x squared. Now to find the bending moment equation, I used the bending moment around point A being equal to 0. I used the bending moment around point B to be equal to 0, which gave me the equation as being m equals 37.68x take away 0.4x cubed. Now to find the maximum bending moment, we know that the maximum bending moment occurs when the shear force equals 0. So we've got the shear force equation here. I've equal to 0, which gave me x as being equal to 5.6 meters. And then we just plug in that x value into the bending moment equation given here, and that would give me the maximum bending moment as being equal to 140.76 kilonewton meters. So I've just summarized what we've already found from the previous page. So here we've got the shear force equation, bending moment equation, and then the maximum bending moment and the zero shear force occurring at x equals 5.6. So I've gone on to draw the shear force and bending moment diagrams. So this is just a diagram of the beam that we've been assessing. It's 9.7 meters long, has a triangular load of 23.31 kilonewton per meter. So here I've given the shear force diagram and I've marked the 5.6 meters as being equal to 0. So I've just have this dotted line to make sure that I communicate that the maximum bending moment did occur in fact at 5.6 meters, which was when the shear force equal to 0. So here's my bending moment diagram. I've just used the sign convention here. I've just switched it around so the positive bending moment is at the bottom or below the line, just so that it gives a much more realistic representation of how the beam would bend under the load. So we're going to move on to calculating the maximum slope and maximum deflection for the beam. So to start off, I've mentioned the Young's modulus for steel, which is what the beam is made out of. Then I've calculated the moment of inertia of the beam, which is given right here, 6.47 times 10 to the negative 3. Then we have from our previous calculations that the bending moment equation is 37.68 times x, take away 0.4 times x cubed. So to start off, we're going to find equations for the slope and deflections with respective to x. So to start those calculations, we've got here that the Young's modulus times the moment of inertia times the second derivative of deflection equals the bending moment equation. So we're first gonna integrate both sides, which on the left hand side here we've got the constant Young's modulus times moment of inertia times we've got this first derivative of the deflection, which equals the slope. And on the right hand side we've got an integration of the bending moment equation. So here I've integrated it and it's a indefinite integral, so we've got a constant at the end. Then we integrate both sides again. When we do that, we just left with the constant times the deflection times the second integral of the bending moment equation, which I've calculated here. Because it is an indefinite integral, we've got a second constant. So now we've got two equations here, and we've got two unknown constants. To find those two unknown constants, we're going to use boundary conditions. So I've listed my boundary conditions here. Because the beam has pin supports at both ends, we know that the deflection equals 0 at x equals 0 and the deflection equals 0 when x equals 9.7. So by substituting the first condition to equation 2, we've got that the second constant C2 equals 0, and by substituting C2 and the second boundary condition to equation 2, we found that C1 equals a negative 413.83. So we're going to substitute the values that we found for C1 and C2 into the equations that are given here, and then we have our equations for the slope and deflection with respect to x. I have kept the Young's modulus and the moment of inertia on the left side of the equation, just because I thought that would be easier for me to just simplify it at the end when I'm finding the maximum slope and deflection. So we've gone on to find the maximum slope next. So using differential calculus, we know that the maximum and minimum values occur when the derivative is 0. And so we already know that the derivative of the slope is the maximum the derivative of the slope is the bending moment. So the bending moment equals to 0 at x equals 0 and when x equals 9.7. So we've found the slope at both those points when x equals 0 and x equals 9.7, which is a negative 3.04 times 10 to the negative 7 and 3.49 times 10 to the negative 7 respectively. So in considering to find the maximum slope, we compare those two values. Although this one has a negative, that really just indicates the direction of the slope, so we're more interested on which of those two values have the highest magnitude, and that is the second value here, 3.49 times 10 to the negative 7, which is at x equals 9.7. So then we find the maximum deflection. So the maximum deflection equals when the slope equals 0. This is again because of differential calculus. When the derivative equals 0, we've either got a maximum or a minimum of the original function. So now to find when the slope equals 0, we've substituted 0. We've used the function that we got earlier right here. So we've equaled it to 0, and using that we've got those values for x. Now we have to keep in mind that x is between 0 and 9.7, and so from those four values we've decided that the correct value is 5.04, as that's the only value that fits in this interval. Now to find the maximum deflection, we just sub in x equals 5.04 into our equation for deflection, and that gives maximum deflection to be negative 9.91 times 10 to the negative 7 meters. This is just a little summary of what we've calculated so far. We've got the maximum slope, 3.49 times 10 to the negative 7, which occurs at x equals 9.7 meters, and then maximum deflection, which is a negative 9.91 times 10 to the negative 7 meters, which occurs at x equals 5.04. So next we are calculating the maximum tensile stress. So before that, I've just listed some of the values that I'm going to need for those calculations. I've just got those from the previous pages. So the maximum bending moment I've got from my diagram here, 140.76 kilonewton meters. Maximum shear force is the one here. Again, the negative sign is only indicative of the direction, not the magnitude. So the maximum shear force is 75.22. And then we've also used the moment of inertia of the beam, which I've calculated here, 6.47 times 10 to the negative 3. So that's what I've listed down here. Then I've got my formula for maximum tensile stress. So we've already got what M is, we've got I, and as for the Y, that is the distance between the neutral axis and the bottom of the beam, which is where the tensile stress is the highest, and that distance works out to be 0.1 meter. So we sub in the values and we get the maximum tensile stress to be 2175.58 kilopascals. Next, we've calculated the maximum shear stress. Again, I've got the the formula for torque here, which I've obtained from our lectures. So the area that we're concerned about is the area below the neutral axis, which is this area that I've shaded right here. So the area of that is 0.02 meters squared. And y bar, which is the distance between the centroid of that area and neutral axis, which works out to be 0.05 meters, and b is the breadth of the cut, which would be 0.2 meters. So we plug in the values and we get 58.13 kilopascals. So now we're going to calculate the maximum principal stress. So I've got the tensile stress here. In the x direction, we know there's no stress in the y direction, as there's no moment in that direction, and we've got no torque at that point, because if we go back to our diagrams right here, we know that when the bending moment is at its maximum, the shear force is 0, so there's no shear stress at that point. So we use our formula right here. I've just copied this from our lectures. I plug in the values and I get the maximum principal stress to be 2175.58 kilopascals per 0. And to find the failure plane, I've just used this formula here, which I've again taken from the lectures, and that works out to be plus or minus 45 degrees. Next, I've calculated the maximum in-plane shear stress, which is given right here. So I'm just gonna go back to my bending moment and shear force diagrams just to make that clear. So the maximum shear force occurs right here when x equals 9.7. So if we go right down, we see that the bending moment at that point is equal to 0. So therefore, what that actually means for our calculations is that there is no tensile stress at that point in the x direction. Of course, there's no tensile stress in the y because there's no moment or stresses in that direction. So we just got this torque or shear stress of 58.13 kilopascals. So to find the maximum shear stress in plane, we've got this formula right here, and it just simplifies as to plus or minus 58.13 kilopascals. So to find the angle or the failure angle, we've got this formula right here, which I've again obtained from our lectures, and that works out to be plus or minus 45 degrees. So that brings us to the conclusion of our video. So here's a summary of all the main calculations that I've done. We've got the maximum slope, maximum deflection, bending stress, shear stress, principal stress, in-plane shear stress, and the failure planes. So in conclusion, I would just like to say it's been a really interesting project to do, and it's definitely increased my confidence in the subject, and I've really enjoyed doing it. Thank you for watching.